Welcome to lecture 19 of EE 720. So let's recap what we did in the previous lecture on primality testing. So the main result which we want to detect whether an integer is a prime or not, an odd integer is a prime or not, is Fermat's little theorem. So what does it say? It says that if P is a prime, and A is any integer not divisible by P, then A raised to P minus 1 should be equal to 1 mod P. Okay. So now we are given an odd integer n and we want to check whether it's a prime or not. So this is our strategy. So what we said was that so if n was an integer, so if you take any integer from 1 to n minus 1, that will not be divisible by n. So if n was a prime, then that integer raised to n minus 1 would be equal to 1 mod n. So we say that choose A in this set. So any integer A in this set will not be divisible by n. And if n was in fact a prime, then uh, you have an integer not divisible by n, so a raised to n minus 1 should be equal to 1 mod n. And so you choose an integer here and compute a raised to n minus 1 mod n. Actually, I should not say this, mod n. A raised to n minus 1 mod n. Now, if this turns out to be not equal to 1, then we know that n is not a prime. So we have two cases. Case 1. If this computation we did, it turns out that the result is not 1, then n is composite. Because it violates Fermat's little theorem. So if n were a prime, then this would have to be equal to 1 mod n, because we are choosing a from this set, and n is not going to divide any of the elements in this set. But if a to the n minus 1 is equal to 1 mod n, then we don't know, we don't get any information. We don't know whether it is about the primality of it. So we get no, we don't know whether n is a prime or not. Okay. So we can choose the integer a randomly from this set and compute this and check. If we get lucky and we see that a raised to n minus 1 is not equal to 1 mod n, then we know that n is composite. And then if a raised to n minus 1 is equal to 1 mod n, then we choose another a and try again, keep trying. Then the question naturally becomes, if I just choose integers from this set, what is the probability that this happens and what is the probability that this happens? So then in the previous lecture, we looked at two cases. We said if the two cases are if A belongs to Zn star or if A does not belong to Zn star. And the results were as follows. So we said if A is not in Zn star, that is if the GCD of A and N is not equal to 1, then n is composite because of the GCD of a and n is not equal to 1, then n has a divisor which is not 1 or n. But when we choose this a, we don't know whether it's in Zn star or not. So we just choose one randomly. So we're not going to compute the GCD. We're just directly going to compute this a raised to n minus 1. So in the previous lecture, we showed that if you this a, if you're lucky and if a falls in outside Zn star, then a raised to n minus 1 is not equal to 1 mod n. Definitely, this is with probability 1, this will happen. But the problem is that issue is integers in Zn star complement are rare. So integers, and we argued that last time. So integers in 1 to n minus 1 which are not in Zn star are rare. There are very few of them. So if you randomly choose an a in this range 1 to n minus 1, it's a very low probability that you will fall on an element, you'll fall, that is, there's very low probability that the a you chose is outside Zn star. So most of the elements will be in Zn star unless n has small prime factors. So we argued that last time also. But if n has small prime factors, then trial division itself will find it easily. So uh, things become interesting only when n is has very large prime factors, like when n is p times q, like in the case of RSA, where p and q are some very large distinct primes, and n is just the product of those two, only two primes. So if a is in Zn star, a to the n minus 1 will not be equal to 1 mod n. But if a is if a is not in Zn star, then this will be true. If a is in Zn star, then we don't know. It may be equal to 1 mod n, or it may not be equal to 1 mod n. So if a is in Zn star, then a to the n minus 1 mod n may or may not be equal to 1. So it doesn't give us any information about the primality of n. If it is not equal to 1, then we know that it is definitely not a prime, but it may be equal to 1 also. So it doesn't give us any information. Then we gave a definition for a witness of compositeness, because we said, okay, elements in Zn star complement are rare. Most of the elements are going to be in Zn star. So we'll define, we'll say that an integer a in Zn star is a witness for the compositeness of n if a to the n minus 1 is not equal to 1 mod. Okay. Because if it's equal to 1 mod n, you don't get any information, but if it is not equal to 1 mod n, you can conclusively say that n is composite. And so we had this theorem. Now the issue is that how many such witnesses do you have in Zn star? Because Zn star complement, all of them are witnesses in some sense, because this will not be equal to 1, definitely not equal to 1. But elements in Zn star may have this, may satisfy this, may not satisfy this. So how many of such witnesses can you have? And I should note that this definition of witness is only when A belongs to Zn star. When we talk about witness, A has to belong to Z. So then there was this theorem which says that if n is if there exists a witness, then there are many of such witnesses, which we proved last time. If there exists a witness, in Zn star that n is composite, then at least half the elements of Zn star are witnesses that n is 1. Okay. And we proved this using Lagrange's theorem, and we showed a subgroup of which contains all the uh, witnesses, or which are not witnesses, and we argued that if there exists a witness, then that subgroup is a proper subgroup of Zn star, so it will be bounded by half the size of Zn star because of Lagrange's theorem. So we did this proof in the last lecture, and I want to repeat that. So now, what is the strategy then? So if somehow we get lucky and we don't even need to know whether this witness exists, but what this witness is. But if this witness exists, such a witness in Zn star exists, then we can have the following strategy. We can just choose t values of a. So we can have the strategy. If witness exists, then strategy for deciding the primality, for checking if n is prime or not. So you choose distinct integers independently and uniformly from 1 to n minus 1. So choose a1, a2 up to some at, some t integers from 1 to n minus 1, and choose them so they are distinct. Uniformly and independently. So randomly choose some t integers, but they should be distinct. There's no point choosing the same integer again because it will not give you any extra information. Then you just compute a1 raised to, then compute a1 raised to n minus 1 mod n, a2 raised to n minus 1 mod n, and so on up to at raised to n mod n, at raised to n minus 1 mod n. Just compute these values. Now, what does the theorem say? So if there is a witness, then at least half the elements in Zn star are witnesses. So you have a situation where if you look at all this is, suppose this is 1 to n minus 1. Now I'm just choosing a1, a2 up to 80 from this set. Now you have this some part of it is Zn star complement. So these, if AIs fall in this, then you'll definitely, it'll know this computation will give you not equal to 1. So if AI falls in this small part, this is a very small part of this, because we said that Zn star dominates this set. So if AI falls in this region, then AI raised to n minus 1 mod n will definitely be not equal to 1. But now, but if AI falls in this region, which is Zn star, the theorem says that at least half of these elements in this Zn star are witnesses. So this is completely, all of these are witnesses, and at least half of the remaining are witnesses. So with a probability which is at least half, AI raised to n minus 1 mod n will be not equal to 1. So with probability at least half, AI raised to n minus 1 not equal to 1 mod n. And we are doing t such tests. So with a probability which is 1 minus 1 bar 2 raised to t, 2 raised to t. So what is this? So what is this 1 by 2 raised to t? This is the probability that, this is the bound on the probability that even when n is composite, you get all of these values give you 1. So what are we trying to check? We are trying to check that n is a prime or composite. If I get not equal to 1 at least for one of these, I know it is composite. So what is the probability that this is not equal to 1? It is at least half. So what is the probability that this is equal to 1? It is at most half. So this probability that this is equal to 1 will be bounded by half. Now what is the probability that all of them give you 1? Basically all of them, n is composite, but you got 1 for all of these. That is 1 over 2 raised to t, because its probability at most half that you get 1 in one of the trials, and in t trials it will be bounded by t independent trials, it will be bounded by 1 over 2 raised to t. So with what is the probability that at least one of these trials give you a number which is not equal to 1? This is 1 minus 1 over 2 raised to t. So with probability 1 minus 1 over 2 raised to t, you will get a number not equal to 1 in one of these places. We can there is a witness or in A1, A2, A2. So with this probability, one of these will give not equal to 1. So there is a witness in these t numbers with probability 1 minus 1 over 2 raised to t. There one of these will be a witness, and you know that n is composite. And if you choose something like t equals 100 or 200, that's only 200 exponentiations. In the last class already I showed you that you can do exponentiations efficiently using square and multiply method. So you do 100 or 200 of these exponentiations, set t equals 100 or 200, and you will check in the sequence of exponentiations, you will look at the sequence a1 raised to n minus 1, a2 raised to n minus 1 up to at raised to n minus 1. With this probability, t equals let's say 100, with probability 1 minus 1 over 2 raised to 100, which is very close to 1, one of these will be not equal to 1, and you know immediately that n is composite. Okay. But the theorem requires, or the hypothesis of the theorem says that this method works, this strategy works only if there is a witness for the compositeness of n in Zn star. So we don't need to know the witness, but there has to exist such a witness. But as I mentioned in the last class, there are numbers unfortunately called Carmichael numbers. So there exist composite numbers for which a raised to n minus 1 will be equal to 1 mod n for all a in Zn star. And these are called Carmichael numbers. So these such n are called Carmichael numbers. And it has been proven that there are infinitely many of these Carmichael numbers. So if you the n, the composite number you're checking for, turns out to be a Carmichael number, in your t tests you'll always get a 1, and you may happily think that, oh yeah, my number is a prime, because if it is composite, then with probability 1 minus 1 over 2 raised to t, one of these t trials should have given a 1, should have given something not equal to 1. But that strategy works only if we are sure that there is a witness for the compositeness of n in Zn star. Otherwise, the strategy will not work. So what do we do? So that's where there is a better test which doesn't require this existence of a witness. It's called the Miller-Rabin primality test, which is what we'll discuss next. So Miller-Rabin. So it takes two integers, two inputs. It takes two inputs, an integer p, and you want to check that p is uh, prime or not, and a parameter t. So this is our candidate for prime and a parameter t. So the parameter t will be in unary format, so 1 raised to t. And this t is going to be the number of iterations. So like in the previous case, we looked at those trials, right? We randomly chose some integers from 1 to n minus 1 and did something. So the t is going to capture that. And this Miller-Rabin primality test, it's going to run in polynomial time, in time which is polynomial. In the bit length of the integer p and t. Okay, so the number of bits in which are used to represent p in binary form. So if p is 17, say, then 17 is, how many bits is that? So I need 5 bits. So let's do this. So how many powers? So it is 16 plus 1. So 2 power 4 plus 1, right? So the binary representation of P is 1, and then 2, 4, 8, 16, right? So the bit length of P is 5 bits. So this Miller-Rabin test will run in polynomial in a time which is polynomial in this bit length of P and the parameter T, which is going to, which you can tune depending on how much confidence you want. So the probability of failure will go down exponentially in t. So it will be 1 over 2 raised to t. So the test will succeed with a probability 1 minus 1 over 2 raised to t, like in the previous case. But the good thing about this test is it doesn't require that existence of a witness. So that uncertainty is not there. So this is going to um, uh, give a more definite result. So we have this theorem. So if P is prime, then the Miller-Rabin test will always output prime. So with the probability 1, it will output prime. So it will identify a prime with a probability 1. But if P is composite, then the algorithm will output composite with a probability 1 minus 1 over 2 raised to t. And output prime, the algorithm I should say outputs. With probability 1 over 2 raised to t. So if it is a prime, there is no ambiguity. It will always output prime. But if it is composite, then there is a small chance of failure. You can make it very small by choosing t large. and the running time is polynomial in t, so it's not exponential in t, it's polynomial in t, so that's good. So you can choose t to be something like 100 or 200, and you get a very high confidence, because with the probability, if you see prime, then either the number is prime, then there's no issues, but if it is composite, then the probability that the algorithm is wrong is only 1 over 2 raised to 100, which is a very small probability. Okay. So let's say I've not described the Miller-Rabin test yet, but suppose we have the Miller-Rabin test as a black box. So given an integer p, it's going to tell us whether it's a prime or composite. And if it says it's composite, it is correct with a very high probability. So using that Miller-Rabin test as a black box, how can I generate a random n-bit prime? So here's the algorithm which is going to use the Miller-Rabin test as a black box. Then we'll look at the Miller-Rabin test itself. So this algorithm, which is going to generate a random n-bit prime, is going to take the length n. How many bits do you want in your prime? And the output is going to be a uniformly chosen n-bit prime. So from the set of all n-bit primes, I'll choose one. I'll give you one. So the algorithm has a loop. So you have a loop, an index which is going from 1 to 3n square. So the 3n square is from Bertrand's postulate, which says that if you look at all n-bit integers, then at least 1 over 3n of them are prime. So if you look at n-bit integers, and at least 1 over 3n of them are prime. So if you choose 3n square of 3n square n-bit integers, the probability that at least one of them is not a prime is e to the minus n. So if you choose these many 3n square integers, because at least 1 over 3n of n-bit integers are prime, so the probability that you don't choose even a single prime will go down exponentially. Okay. So here you're going to loop through this index 1 to 3n square. So you're going to do something 3n square times. Every time you're going to choose a n minus 2 bit string, n minus 2 length bit string. So p prime is going to be a bit string which has n minus 1, n minus 2 bits. Then you're going to prepend a 1 and append a 1. This is a bit 1 here. So if p is this here this double bar is the string concatenation operator. So if I concatenate 1 concatenated by this n minus 2 length bit string and concatenate the 1, this makes sure that the integer is odd, because if it's an even integer, then it is definitely not a prime, except for the integer 2. So this makes sure that this p is odd, and this is the most significant bit. So finally we want an n bit prime. So the most significant bit has to be 1. So this ensures that this p, the candidate, is an n bit integer, and later we'll check using the Miller-Rabin test. We'll run the Miller-Rabin test on p to check whether it's a prime or not. And if the output is prime, the output of the Miller-Rabin test is prime, then we'll just return this integer p here. But if for all these, if this loop actually is body ends here, so for all these 3n square iterations, if I don't return p, if I don't return an integer, then this statement here will execute, which is going to return a fail. So if all 3n square in all 3n square iterations, if the Miller-Rabin test output is composite, so this if condition is not satisfied, then this loop will just run for 3n square times without returning any integer. Then it will just the algorithm will return fail. But by Bertrand's postulate, the probability that the fail is returned is going to be exponentially small in n. So that is going to be the strategy. So Miller-Rabin test is a black box as of now, and now we will look at how the Miller-Rabin test itself works. So before we look at the Miller-Rabin test, or to motivate the Miller-Rabin test, let's look at a lemma which says that if it talks about the square roots of 1. So we say that, so we'll define first. So we say that x and z n star is square root of 1 modulo n if x square equals 1 mod. And if n is an odd prime, so the lemma says that if n is an odd prime, then the only square roots of 1 modulo n are plus or minus 1 mod n. And so what we're going to do, what is this minus 1 here? So minus 1 is going to be n minus 1. So n minus 1 will be equal to minus 1 mod n. So when we say minus 1, we actually mean n minus 1. So the only square roots of 1 mod n are going to be 1 and n minus 1. So because 1 square is definitely 1 and n minus 1 square is so n minus 1 square is going to be n square minus 2n plus 1, which is equal to 1 mod n. So these two are definitely square roots, that is 1 and n minus 1 are definitely square roots of 1 mod n. But what the theorem says is that these are the only square roots. So we know that there are at least 2, but this theorem says that there are only 2. These are the only 2 square roots of 1 mod n. Okay. So let's prove the lemma. So recall that there was this proposition I think it was proposition 8.3. It says that if P is a prime, and P divides A times P, then P divides A or P divides P. We're going to use this proposition here. So what do we have? So we want to show that the only square roots of 1 mod n are 1 and minus 1. So suppose x belongs to Zn star, but this is the x is those elements in this set for which GCD of x and n is 1. But suppose this is the largest set anyways, and suppose x square is equal to 1 mod n. Okay. Then n divides x square minus 1. Right? Because if x square is equal to 1 mod n has to divide the difference between these two integers. So n divides x square minus 1. So this implies n divides x minus 1 times x plus 1, because we can factor x square minus 1 as x minus 1 into x plus 1. Now we are ready to use the proposition. So the lemma says that n is an odd prime. So if it's a prime, then if it divides a product of integers, then it has to divide one or the other. So which implies n divides x minus 1 or n divides x plus 1. Okay. Now if you look at these integers, x minus 1 and x plus 1, x is in 1 to n minus 1. So x minus 1 belongs to 0 to n minus 2, and x plus 1 belongs to 1 to n. Right? So if n has to divide x minus 1, here the only integer n divides is 0. So x minus is equal to 0, which means x equals 1. Or now if n divides x plus 1 and x plus 1 belongs to this set here, the only integer n divides here is n. So x plus 1 is equal to n means x is equal to n minus 1, which is equal to minus 1 mod n. think that got cut off, so let me say it again. So if n divides x minus 1, then if you look at this set here, the only integer n can divide is 0, so which means x minus 1 is equal to 0 means x equals 1. N divides x plus 1, x plus 1 belongs to this set, the only integer n can divide in this set is n. So if x plus 1 equals n, x is n minus 1. So which is also equal to 1 minus 1 mod n. Okay. So we have proved the theorem that if n is an odd prime, the only square roots of 1 modulo n are plus or minus 1 mod n. Okay. So the Miller-Rabin test is going to be based on this lemma here. So let's see. Okay. So n is suppose n is an odd integer and you want to check whether it's a prime or not. So suppose first n is odd. So suppose n is an odd prime. Then we know that by Fermat's little theorem, a raised to n minus 1 equals 1 mod n for all a in 1, 2 up to n minus 1. Right? This is Fermat's little theorem. Now let's look at n minus 1 here. If n is an, I should say, odd prime. So if n is an odd prime, n minus 1 equals some power of 2 times u, where because n is odd means n minus 1 is even. So this power r, so this is even. So at least r should be greater than or equal to 1. It's an integer which is greater than or equal to 1. And if you accumulate all the powers of 2 in n minus 1 into this here, u is you can make u an odd integer. Yeah. So like for example, so suppose n equals 11, then n minus 1 is 10, which is 2 times 5. So r is 1 and u is 5. N is 17, then n minus 1 is 16, which is 2 power 4 times 1. So the odd integer u can be as small as 1, but you can always represent n minus 1 as some power of 2 times an odd integer, where that power is r is at least 1, because this is an even integer, so at least you'll see 2 times something. Like in this case here, you saw 2 times 5. Okay, so how does this help us? So now if you look at a sequence like this, let me turn the page. So you have n minus 1 is 2 power r u, where r is greater than or equal to 1 and u is odd, right? Now if you look at this sequence here, a to the u mod n, a to the 2 times u mod n, a to the 2 square times u mod n, and so on up to a to the 2 raised to r u mod n. So a to the u mod n, a to the 2u. So the exponent is doubling, which means that if I square this, I'll get this. If I square this, in the exponent, u will be multiplied by 2 and I'll get this. If I square this, I will get this, because in the exponent, this 2u will be multiplied by 2, I'll get 2 square. So I keep squaring. So I take this first modulo result here and I keep squaring it modulo n, and I'll get all the this whole sequence here. And this final exponent is n minus 1, because n minus 1 was equal to 2 power r u, right? So this has to be 1. Right? This is 1. Now what does the lemma tell us? So we've already assumed that n is an odd prime. What does the lemma tell us? The square roots of 1 modulo n, when n is an odd prime, can only be 1 or minus 1. Right? So these are a sequence of squares. So if I look at this element, this element is the square root of this element. And this element a to the u mod n is the square root of a to the 2u mod n, because squaring this gives this. So in this sequence, the preceding element is the square root of any element here. So if the last element is 1, so the preceding element can be only 1 or minus 1, right? So it can happen that if I look at this sequence, the sequence can be like this. It can be that 1, then the preceding element can again be 1, preceding element can again be 1. But then if I get a minus 1 here, then I don't know what this is. This can be anything. Because the lemma doesn't say what the square root of minus 1 is. It only says what the square root of 1 can be. The square root of 1 modulo n can be only 1 or minus 1. So if I start from, for any a, the last element in this sequence of squarings is 1, because a raised to n minus 1 mod n is 1 by Fermat's little theorem. But if you look at the square roots, the square root of 1 can be 1 or minus 1. It can, if it is the square root of 1, the last element 1 is 1 again. So here I'm talking about the square root of a raised to so if a raised to 2 to the ru is 1 mod n, I'm not taking this, then this, the square root of that guy can be 1 or minus 1. So I get 1, but if I get minus 1 at some point, that is if a raised to 2 square u is minus 1, then I don't know what the square root of that is going to be. So once I get a minus 1, then I don't know what these elements are. So these could be anything. So it is so if n is an odd prime, you will see a sequence like this. It can happen that this whole sequence is all ones. It can happen that 1 comma 1 comma 1 and all of these. Squaring this just gives you all ones. But whenever you get a minus 1, then the remaining part is unpredictable. It can be something like minus 1. Sorry, that got cut off. So it can be 1 1 1 all the way is ones. It can be minus 1. It can start with a minus 1, and then it can be ones all the way. But if a minus 1 appears anywhere, somewhere here, then all the preceding elements, we don't know what they are. They can be anything. They can be 5 or 11 or anything. They can be anything. So this is the structure. If n is an odd prime, this is the structure we'll see. So let me just repeat it again so there's no confusion. So we are actually computing this in the forward direction. So we calculate n minus 1, it is 2 power r u, and then you choose some a which is from 1 to n minus 1, and then you're computing a raised to u mod n, a raised to 2u mod n, and so on. So these, so what my claim is that, so the last element in the sequence has to be always 1. If n is an odd prime, it always has to be a 1. Now, how does the preceding elements, how can they look like? Because each element is you're getting, by squaring the each element, you're getting the next element. So this element is the square root of its successor. So in this sequence, the last element is always going to be 1. So it can happen that all of them are 1, and that's how you get 1 at the end. But if all of them are not 1, it has to happen that a minus 1 has to appear, and then it will eventually lead to a 1. When a minus 1 appears, squaring it will give you 1, and all the remaining are 1. So either you have all ones. If you don't have this sequence, then it has to happen that the first non-identity, if you look from the right, the non-1, if you look from the right, it has to be a minus 1, and only then some other numbers can appear. Because the square root of 1 modulo n, when n is an odd prime, it can only be 1 or minus 1 by the lemma here. So how are we going to use this to do primality testing? So this kind of structure is guaranteed only if n is an odd prime. So let me write that. So this kind of a pattern if n is an odd prime. So if there is a deviation from this pattern, then we know that n is composite. So what kind of deviation can happen? Suppose the square root of 1, the element before this, if it turns out to be not equal to 1 or minus 1, let's say n is, let's say, a large prime and this turns out to be 5, then we know that if n is very large, then let's say n minus 1 is not 5, then we know that uh, n cannot be a prime because the square root of 1, so instead of minus 1, if I see a 5 here, then I know that that is not a n is not a prime. So any deviation from this pattern will reveal that n is composite. So deviation from this pattern reveals compositeness. Confirms So what does deviation mean? So we'll say that, so let's capture this pattern here. So if n is an odd prime, only one of two things can happen. So this pattern I'll capture precisely like this. So for prime n, so what are the two things? So either a to the u, so n minus 1 is 2 raised to r times u, where u is odd. So this is equal to plus or minus 1 mod n. So this was the case like this. So either the first power a to the u mod n is either 1 or minus 1, and after that you see only ones everywhere. So that can happen. Or one of these has to be minus 1. So if this is eliminated, all ones is eliminated, then at least one minus 1 has to appear. So either the minus 1 appears right at the beginning or somewhere in the middle. So that's what the second condition is going to say. Or one of a to the 2u mod n. So a to the u is the first, a to the u mod n is the first one. So either we're saying either it is plus or minus 1, which means all the remaining elements are 1 remaining because of their squarings of this, or one of the remaining squares, a to the 2 square u mod n all the way up to a to the 2 to the r minus 1 u mod n is equal to minus 1. Okay. Yeah, because why am I not considering 2 to the ru? So if n is a prime, then a to the 2 to the ru, n minus 1 is equal to 2 to the ru. So a to the n minus 1 must be equal to 1. Sorry about that. So n minus 1 is 2 to the ru if n is an odd prime. So a to the n minus 1 must be equal to 1 mod n. Okay. So in this, if n is an odd prime, then this is anyway guaranteed. But what else must happen? So either you start with a 1 and you see all 1, 1, 1, 1, or you start with a minus 1 and remaining ones are all 1, or at least one of these guys has to be a minus 1. And after that minus 1 appears, the remaining elements in the sequence have to be 1. So for prime n, not prime n, one of these two things has to happen. So if these two don't happen, then we'll say that integer a is a strong witness that n is composite. So let me turn the page. So we say that a in Zn star is a strong witness that n is composite if both the above conditions don't hold. So explicitly what that means is, if they don't hold, what does that mean? We want a to the u is, so first we want a to the u is not equal to plus or minus 1 mod n, and a to the 2 raised to I u is not equal to minus 1 mod n for all I in 1 to r minus 1. Okay, so these are the two conditions for something to be a strong witness. So what was a witness again? So recall witness definition was A in Zn star was a witness for the compositeness of n if a raised to n minus 1 was not equal to 1 mod n. This was the witness definition. So if A is a witness, then A is also a strong witness. Okay, and we can argue it like this. So suppose A is not a strong witness. Suppose A is not a strong witness. Then what does that mean? So the definition of strong witness is that either this is true or this is true. If it is not a strong witness, if it is a strong witness, either this is true or this is true. Sorry, and this is true. I should not say either. If A is a strong witness, then both of these have to be true. If it is not a strong witness, so either A raised to U is equal to plus or minus 1, or this is true. Okay, so let me repeat that before I change the frame. So if it is not a strong witness, then it's a negation of a conjunction here. It's an and of two statements. So negation of this is negation of this or negation of this. So what is negation of this? I'll replace a not equal to with equal to. And negation of this is this is saying that a raised to 2 raised to a to the 2 raised to I u is not equal to minus 1 for all. And the negation of this will be that for one of these indices, I'll get a equals here. So let me write that. Then either a raised to u is equal to plus or minus 1 mod n, or for some I in 1 2 up to r minus 1, we'll have a raised to 2 to the I u is equal to minus 1 mod n. Okay. So what are we trying to do here? We are trying to argue that if A is a witness, then A is also a strong witness. And what is the definition of witness? A raised to n minus 1 is not equal to 1 mod n. Now we're trying to argue by contradiction. So if A is not a strong witness, then this is true or this is true. But if this is true, then if this is true, then A raised to 2 raised to u, which will be A raised to n minus 1. So if this is true, then A raised to 2 raised to u is just, let me write it explicitly, A raised to u whole raised to 2 power r, which is A raised to 2 power r u, which is Oh wait, uh, that I don't need. So this is equal to 1 model, right? Because if this is true, it's either plus or minus 1, and we said r is greater than or equal to 1. So a raised to 2 raised to u. Let's scratch out the 1 also. Sorry. So a raised to 2 raised to ru will be a raised to u whole raised to 2 raised to r. This is at least one even 1 power of 2 here, so it's 2 or 2 square or 2 power 4, 2 power 2 cube and so on. So minus 1 raised to any even power will just get 1. 1 raised to even power, any power is 1. So if this is true, then a raised to 2 raised to r times u is 1 mod n, which implies a raised to n minus 1 equals 1 mod n, which contradicts the witness that a being a witness, right? Similarly, you can argue that if this is true, then 2 raised to I is from 1 to r minus 1. So 2 raised to r will be at least a square of this, if not some higher power of this, some higher even power of this. So you'll get a raised to n minus 1 equals 1 mod n in second case also. So this contradicts a being a witness. So this shows that if A is a witness, and A is also a strong witness. So let's just do it again quickly. So if A is a witness, A is also a strong witness. Suppose A is not a strong witness, then one of these two has to hold, and then that contradicts A being a witness, because I'm getting A raised to n minus 1 is equal to 1 mod n again. So we can, but if A is a strong witness, then it may not be true that A is a witness. So there can be more strong witnesses than witnesses. So the Miller-Rabin test will depend on this fact here, that if we can find even one strong witness, then we are sure that N is composite. So if we can find even one strong witness, we can conclude N is composite. So basically, it's a deviation from the pattern one would expect if N is not prime. So, so how many such strong witnesses are there? So for that, let's define first something called a prime power. So we say that an integer n is a prime power if n equals p raised to r, where r is greater than or equal to 1. So, and p is a prime. So a prime is also a prime power, because r equals 1 is allowed. So if n is a prime, n is equal to p raised to 1. So you can consider it as a prime power. But higher powers are also, so n can be p square, where p is a prime, or p cube, p raised to 3, and so on. Okay, so those are called prime powers. So the theorem which tells us how many strong witnesses can there be is here. So let n be a odd number, integer, that is not a prime power. Okay, then at least half the elements of Zn star are strong witnesses that n is composite. Okay. So what is prime power again? Prime power is n is, if n is called a prime power if n is p raised to r, where p is a prime. Now, if n is not a prime power, then it can't be prime also, because primes are also prime powers. We are allowing r to be 1. So if n is a composite number that is not a prime power, it is not a prime also. Then at least half the elements in Zn star are strong witnesses that n is composite. But then you might ask that what if the hypothesis of this theorem is not satisfied? So how can it not be satisfied? So it's before we do the proof, suppose n is of the form some p cube. Okay, then n is a prime power. So then this hypothesis of this theorem is not satisfied, because this theorem holds for only when n is not a prime power. So if n is equal to p cube, this theorem will not work. But then this theorem does not hold. And if suppose n is equal to p, where p is a prime, then again this is a prime power, because the prime power is n is p raised to r, where r is greater than or equal to 1. Then the theorem does not hold. But we want to differentiate between these two cases. Here n is a prime, so this is the case we want to identify. Now here n is not a prime power, but it is n is a prime power, so it doesn't the hypothesis of the theorem does not hold. So I want to remove cases like this. I want to identify cases where uh, n is composite, and but still the conditions of the theorem do not hold, or the hypothesis of the theorem does not hold. So how can I identify such cases? That is, how can I identify, or how can I differentiate between these two cases? I want to differentiate between cases when n is p raised to some prime power, and the cases where n is prime. So why do I want to differentiate between these two cases where this condition of this theorem does not hold? Because what is this theorem telling us? That it's saying that if n is an odd integer that is not a prime power, then at least half the elements of Zn star are strong witnesses. So now, as before, as the strategy we had before, if I randomly choose elements from 1 to n minus 1, then and if I check that are they strong witnesses or not, then with the probability half, I land on an element which is not a strong witness if n is composite. Okay, so if n is prime, then no strong witnesses exist, because n is prime. These witnesses are for the compositeness of n. So if n is prime, I don't need any guarantees. But when n is composite, I need to guarantees that I want to fall on strong witnesses. So when n is composite is when I want to check for the condition of this theorem. And that is the cases like this. So I want to eliminate cases like this where n is composite, but it is a prime power. So I want to, so that I can apply this theorem here. So for that we'll use an algorithm which can identify perfect powers. So an integer n is a perfect power if n can be written as n hat raised to e for integers n hat and e greater than or equal to 2. So n is a perfect power. So it is some integer raised to e. The difference between prime power and this was that the first of all the base was prime there, and that exponent was greater than or equal to 1. But here I want it to be greater than or equal to 2. So can I identify that an integer is a perfect power? So it turns out that there is a polynomial time algorithm to check whether an integer is a perfect power. So there exists a polynomial time algorithm to check if a given integer is a perfect power. So the algorithm is outlined in exercise 8.12 in Katz and Lindell, but I will just give some intuition of how it works. Okay, so suppose we want to check that something is a perfect power or not. Suppose we want to check if n is some n hat raised to e for integers n hat and e greater than or equal to 2. Now if n is this double bar n bits long, then n is less than or equal to 2 raised to n. It should be strictly less than, but this is okay. So for example, suppose n is 5, then the binary representation of n is 101, right? 1, 2, 4, 4 plus 1 is 5. And the number of bits in n is 3. The description of n is 3. And 5 is n, which is uh, less than 2 raised to 3, right? Which is 8. So we have n will always be, you can say strictly less than 2 raised to number of bits in n. Okay. So now if you look at so if n is equal to some n hat raised to e, and that is less than 2 raised to this. So this means that for n hat greater than or equal to 2, this exponent has to be less than or equal to the number of bits in n. Makes sense, right? Anyway, when the base is 1, then n is equal to 1. So that is like a trivial case. Let's not even consider that. So if the base is at least 2, now this n, if I want to check that n is a perfect power. So in case n is a perfect power, it will be some base raised to some exponent e. Now if that base is at least 2, this exponent has to be at most this, right? Because if I'm increasing this, now this can only decrease. This can't be larger than this, right? Because then you'll violate the bound here. So this, the exponent is bounded by the number of bits in n, uh, which is logarithmic. So this is the number of bits in n will be of the order of log n, right? Uh, so so what we do is that given n, I want to check whether it is a perfect power. First, calculate the square root using real arithmetic. Using real arithmetic, just compute the square root of n. If you get an integer, if there exists an integer such that n is equal to n hat square, so then we know that n is a perfect power. First check if square root of n is an integer. If not, check if cube root of n is an integer. So this is real arithmetic. So this can be done in time which is polynomial in the number of bits in n. So keep checking that. And how many should we check? Well, the exponent can be at most number of bits in n. So you need to check up to the eth root of n. Okay, not eth root of n. This mod number of bits root of n till the okay. So this can tell you whether n is a perfect power or not. So you need to check only the number of roots you're calculating is bounded by the number of bits in n, which is so finally this algorithm will terminate in time which is polynomial in the number of bits in n, the description length of n. Okay, so it's a polynomial time algorithm. So suppose we have an algorithm now. So an algorithm which can check if it is a perfect power or not. Now our theorem says that if n is not a prime power, then at least half the uh, half the elements in Zn star are strong witnesses. So here are some observations. So if n turns out to be a perfect power, that is n is equal to n hat raised to e for e greater than or equal to 2, then n is composite. You're done. So then there's no primality testing required. You're already checked whether this is your primality test. In fact, so this you already know it's a composite because you have factors. It's n hat into at least n hat into n hat because e is greater than or equal to 2. So if I can first in polynomial time, I'll check whether n is a perfect power. So if it turns out it's a perfect power, then I know that n is composite and I'm done. We turn the page. So if we run our algorithm for checking if n is a perfect power or not, so if n turns out to be not a perfect power, if n is not a perfect power, then there are two cases. Then what is it? N is not equal to some n hat raised to e for any n hat and e greater than or equal to 2. So that's what it means for it not to be a perfect power. So then what are the cases? So one possibility is that n could be prime, because we said e is greater than or equal to 2. So it can be that n could be just some equal to some prime. But for our test, when n is prime, we don't need any guarantees about the number of strong witnesses. But if n is not if it is not prime, it cannot be a prime power. That is, n cannot be equal to p raised to r for r greater than or equal to 1. Why is that? Because n is already not a perfect power. We checked it using a polynomial time algorithm. N could be prime. Then we actually don't care about that case, because if n is a prime, we don't care about the number of strong witnesses, because we only are worried about identifying composite n. But if n is not a prime, it is a composite number, then it cannot be a prime power, because that is, it can't be of this form. Because if it is of this form, this algorithm would have identified that P and R, that algorithm for checking all the eth roots from e going from 2 to the bit length of n, would have identified P and R. So what we'll do is that we'll check whether n is a perfect power. If it's a perfect power, it's composite. If it is n is not a perfect power, then we proceed with randomly choosing elements from 1 to n minus 1 and seeing if they're strong witnesses. and we are guaranteed that at least half of Zn star will be strong witnesses because n is not a prime power. Okay, so I'll just describe the Miller-Rabin test, which is going to take advantage of this perfect power test and the number of strong witnesses. So the input to the Miller-Rabin test is going to be an odd integer, which is some n, and a parameter t, which is going to capture our confidence level. How confident do we want to be about the uh, primeness of n? So when we get a decision, the output is a decision whether n is prime or composite. Okay. So first step is you check whether n is a perfect power. So like I said, you just calculate the square root of n, cube root of n, up to the uh, some eth root of n, where e is the number of bits in n, and check whether any of those are integers. If any of those are integers, you know it's a perfect power and it's composite. So you were done. It return composite. Otherwise, you calculate n minus 1. N minus 1 is going to be some power of 2 times u, where this there should be at least one power of 2. So r is greater than or equal to 1. This 2 power r times u. And this looks like a little m. And then you run a loop like in the previous test. So you're going to run some j from 1 to t. The t's are going to be the trials here. So this you're going to randomly pick an integer a from this range 1 to n minus 1, and you're going to check if the pattern deviates from what you would expect from if n were prime. So if a is not equal to plus or minus 1, and if a is not equal to 2 raised to ui minus 1 for all these i's from 1 to r minus 1, then you return composite. And you run this for t trials, and if in all these t trials we don't return composite, then at the end of the t trials you return prime. So that is going to be the Miller-Rabin test. Now coming back to the theorem, which said that if n is an odd prime, then so that is the main thing. That so this is going to check if something is a strong witness or not. So you want to so how confident can we be in this check? That is, what is the probability with which if n is composite, this um, algorithm will return prime. So that theorem, it says that at least if, so let me just repeat the theorem here for completeness. Let n be an odd number that is not a prime power. Then at least half the, I'll say half of Zn star are strong witnesses. That n is composite. Okay. So this theorem is it's theorem 8.40 in the book. So I encourage you to look at the proof. I'm going to skip the proof, maybe due to time reasons, because this lecture is already gone on for too long. So this theorem, it gives us confidence that so if n is prime, then this pattern will always be violated, and we'll never return composite. But if n is composite, we are saying that, and we already checked that it's not a perfect power. If n is composite, and if it is not a perfect power, then it is not a prime power. So this will be this the hypothesis of this theorem is satisfied, and at least half of Zn star are strong witnesses. So with the probability if we do t trials, then with the probability half in each trial, I'll return composite. So the probability that I don't return half in all the t trials will be bounded by 1 over 2 raised to t. So we'll get that is how we get a very high degree of confidence that this Miller-Rabin test will return. When it returns prime, then it can only fail with a probability which is bounded by 1 over 2 raised to t. Okay. So again, this is theorem 8.40 in Katz and Lindell. So you can look at the proof there.